Good morning. Our today's topic is arithmetic and instruction pipeline. Okay, in the last class we have discussed about pipeline, right? I have introduced what is pipeline and how any operation that need to be performed can be divided into sub operations and can be processed, okay, in pipeline systems that we have discussed in the last class. Okay, pipeline is a technique of decomposing a sequential process into sub-processes. And in computer systems, this pipeline can be applied in two areas. One is arithmetic operations, okay, during arithmetic operations, and the other one is during the execution of instructions. So when an arithmetic operation is performed, that can be used where the operation can be subdivided into sub-operations. The arithmetic operation can be divided into sub-operations and can be done in different segments. Okay, that is called arithmetic pipeline. The pipeline unit that is used to divide the arithmetic operations into sub-operations, okay, and perform these tasks, arithmetic sub-operations parallelly, okay, at the same time in different units. That is arithmetic pipeline. An instruction pipeline allows the computer to process or execute the instructions, okay, instruction phases, different phases parallelly. The instructions that is being executed in the computer, we know that it has different phases, right? Every instruction cycle consists of different phases. Okay, so these phases can be run in different segments and can be done parallelly. Many instructions can be executed parallelly. Okay, so that the pipeline unit that supports that is instruction pipeline. Okay, the pipeline unit that support arithmetic operations to be performed parallelly, to be done parallelly are arithmetic pipeline, and the pipeline unit that supports instruction execution parallelly is instruction pipeline. So here arithmetic pipeline. These arithmetic pipeline units are used in very high speed computers. Okay. Okay, the operations that can be divided into sub-operations, such as floating point, addition, subtraction, multiplication and division, and even multiplication and division of fixed point numbers and similar computations. Okay, to do these kind of computations, we use arithmetic pipeline. So here let's take an example of a pipeline unit for floating point addition and subtraction. Here x and y, we have taken two numbers x and y. These two are floating point binary numbers. Okay, x equal to a into 2 power a and y is y equal to b into 2 power b. These are the two floating point, normalized floating point binary numbers. Okay, where a and b here are two fractions that represent the mantisas. A and b are mantissa part of this number, and this small a and small b are the exponents. Okay, so to carry out this floating point addition or subtraction, this operation can be divided into sub-operations, 4 sub-operations that are performed in 4 segments. So what are the sub-operations? How we can divide this operation of adding or subtracting these two floating point numbers? What is the first thing we do? We compare the exponents, right? For performing addition or subtraction, the exponents need to be same. So we compare the exponents. So the first sub-operation is comparing the exponents. And based on that, we choose one exponent, right? Okay, and the mantissa need to be aligned to make the exponents equal. A need to be equal to B. So aligning the mantissas, okay, to make the exponents equal to perform this addition or subtraction. So the second sub-operation is aligning the mantissas. Okay, compare the exponents, then align the mantissas. The third operation is once the exponents are equal, okay, add or subtract the mantissa depending on the operation specified. If it is add the mantissa part of these two numbers. Or if it is subtract the mantissa part of these two numbers. So you obtain the result. And the fourth sub operation is normalize the result. Here normalizing means there may be overflow. When we perform addition, there may be overflow. Same way during subtraction, after subtraction, the result may have underflow. Okay, that is identified by before the decimal point. The digit that comes before the decimal point should be 0 in the result. Okay, if it is some other digit, we need to shift the entire number to right. That can be done by shifting the mantissa digits right to right and adjusting the exponents. Correct? And the digit that comes after the decimal point should not be 0. So if there is 0, we need to shift the digits to left, okay, and adjust the exponent accordingly. Okay, so that is normalizing. That means there is underflow. Okay, so we shift the digits to left and adjust the exponent. So that way we normalize the result finally. Okay, so this way, these four sub operations, the floating point addition and subtraction, can be divided into four sub operations. Compare the exponents, align the mantissas, add or subtract the mantissa, and normalize the result. So here this flow chart shows this. At the left side, we have small a and b. What is small a and b here are the exponent. This is the exponent, and here is the mantissa, capital A and B. Okay, so here we have divided these operations into four sub operations. So segment 1 executes the first sub operation, and segment 2 does the second operation, segment 3 and segment 4. Okay, so there are four segments that performs these sub operations independently and parallelly. Here the operation that is to be performed is, the task that is to be performed is addition or subtraction of these two floating point numbers. To complete it faster, we have divided into sub operations and performing these operations in different segments. So here exponents a and small a and b are stored and registered first, and then these exponents are compared. That is the first sub operation, compare the exponents. Okay, these two exponents are compared. How we compare it? A minus b is done. Okay, so subtraction is done. When a minus b is performed, okay, if the result is positive, means a is greater than b. If the result is difference, here we get as negative, means b is greater than a. Okay, so once this difference is identified, okay, once the exponents are compared, we choose the exponent. So the next sub operation is choose the exponent and accordingly align the mantissa. So by aligning, we make the exponents equal. And once this is done, that is stored in the register R here. Okay, and segment 3 performs the third sub operation, that is addition, performing addition or subtraction of the mantissas. So add or subtract mantissas and store the result in register. Now we need to normalize the result, the final sub operation that is performed in segment 4. That is normalizing the result. If the digit before the decimal point, okay, it should be 0. So if not, if it is some other digit, we shift right, or if the digit after the decimal point is not 0, we shift it left. Okay, and accordingly adjust the exponent. Okay, this way we normalize the result, and the final result will be stored in the mantissa is in this register R, and the final exponent will be in register R here. Okay, so this way we get the final result of this floating point addition or subtraction. So let's take an example. Let's say x here is 0.9 0.9504 into 10 power 3, and y is 0.8200 into 10 power 2. Okay, so the two numbers we have taken here are x and y. X is 0.9504 into 10 power 3 and y is 0.8200 into 10 power 2. So the first operation here, okay, here in the pipeline, it's the pipeline operations in different segments, okay, that is shown here. What are these exponent? Exponents are 3, A is 3 and B is 2. Okay, and the mantissa are 0. What is capital A? 0.9504 and B is 0.8200. So the first sub operation is compare the exponents. We compare the exponents. So perform by subtraction. So we perform 3 minus 2. The result is difference is 1 here. Okay, that means it is positive, means the first A is greater than B. Okay, so that A is chosen as the exponent here. Okay, what is A here? The exponent chosen is 3. Okay, and align the mantissas. Okay, accordingly we need to align. So this B, yeah, the mantissa part of Y, that is 0.8200 need to be shifted right? Okay, so this becomes 0.0820 into 10 power 3, correct? So only we are taking the considering the mantissa part here. So it is shifted to 0.820. 0 and the mantissa exponent chosen is 3. Now the third sub operation that is performed in segment 3 is add or subtract. So let's say it is addition. Okay, so the addition of these two numbers are done here. 0.9504 plus 0.0, we have adjusted, aligned the mantissa. So it is 0.820. Okay, when you add 4, 2, 3, this is 1.0324. Okay, so that will be there in result, that is stored in register R. Okay, this is the result that gets stored in R after addition. And the next segment, okay, segment 4. In segment 4, the operation performed is normalize the result. So here it is, there is an overflow after addition of these two numbers. Okay, there is an overflow. We say there is an overflow because the digit that comes before the decimal point is 1 here. Okay, so we shift this to right. When we shift it to right, it becomes 0.1032 into, okay, this is the mantissa part is this, okay, 0.10324, and the exponent need to be adjusted. As we shifted this to right, exponent becomes 4, correct? It need to be incremented. We have shifted it right here. So exponent is 4. So finally in register R, we will have exponent, okay, 4 as the exponent and this as the mantissa, the result, final result. Okay, so the result of x plus y here is 0.10324 into 10 power 4. Okay, so this way, but here as these operations, okay, this entire operation of performing addition and addition or subtraction of these floating point numbers are divided into sub operations. All these operations can be done parallelly. So how much time this will take? Okay, if we compare the time that is taken by this pipeline unit, okay, the system that has this pipeline unit, and we compare it with the non-pipeline system, let's say the time taken by the segment 1 is T1. Okay, we refer it as T1. It is 60 nanoseconds. And the time taken by segment 2 is T2, that is 70 nanoseconds. And let's say segment 3, to perform this addition and subtraction, the time taken is T3, it's 100 nanoseconds. And segment 4 takes, the time taken is T4, that is 80 nanoseconds. Okay, and the registered, for storing these results into registers, okay, the time delay is TR. We refer it as TR. I'm writing it here. TR is 10 nanoseconds. Okay. As these operations are done parallelly in this pipeline unit, these operations are done parallelly. If we take this, okay, let's assume that this is the maximum time taken, T3, that is 100 nanoseconds. And to transfer the results to registers 10 nanoseconds. So 100 plus 10, it is the time in pipeline system, okay, it is referred to as TP, is 110 nanoseconds. In pipeline system, okay, the time taken is, clock cycle time is 110 nanoseconds. Okay, in a pipeline system, the time taken is 110 nanoseconds. And if it is a non-pipeline system, okay, non-pipeline system, these operations cannot be done parallelly. Let's say if the first operation takes 60 seconds, T1, 60 nanoseconds, and second operation takes 70 nanoseconds, third operation takes 100 nanoseconds, and fourth take 80 nanoseconds, and for shifting it to registers, the time delay is 10 nanoseconds. So totally the time taken would be T1 plus T2 plus T3 plus T4 plus TR, okay, to transfer to register TR. So it is, if we calculate that, it is 320 nanoseconds. Okay, so this is the difference here. The speed up ratio is Tn by Tp, right? The speed up is S is 320 nanoseconds by 110 nanoseconds, which is 2.9. Okay, so this means, what does this mean? The pipeline, the ratio, speed up ratio of pipeline system, okay, over a non-pipeline system is 2.9. Okay, means it is 3 times faster than the non-pipeline system. Performing these operations parallelly, dividing into sub-operations and running in pipeline unit is 3 times faster than performing the same operation in a non-pipeline system. Hope this is clear. We'll move on to the next one, instruction pipeline. So this way, using arithmetic pipeline, the arithmetic operations, okay, what all the arithmetic operations that is performed in ALU, they can be pipelined to be executed parallelly to speed up the process. Okay, this way the process can be, the arithmetic operation, performing the arithmetic operation can be done faster. And the second type of pipeline is instruction pipeline. Okay, this instruction pipeline is used to speed up the instruction execution. We know that instruction execution consists of different phases, right? So if we divide it into smaller phases, okay, the phases of this instruction cycle are: fetch the instruction from memory. This is the first phase. And once the instruction is fetched, fetching means transferring from memory to instruction register, right? From memory address, the given address, okay, from there to transferring it to instruction register in CPU, that is fetching. And then second phase is decoding. Decoding is finding the meaning of the operation, dividing the instruction into different subparts. Like the operand, it consists of operands and the operation to be performed. So finding the meaning of it. Okay, what is the operation to be performed? And the third phase of this instruction cycle is calculate the effective address. Okay, there may be the address given may be an indirect address. That case, effective address is the direct address. So if in case the address given is indirect address, the effective address need to be calculated. So that is the third phase. Then once the effective address is calculated, we can fetch the operands from memory, okay, from the effective address calculated. This shows the effective address shows the location of the operands. So fetching the operands from memory, that is the fourth phase of the instruction cycle. Once the operand is fetched, the instruction is executed using the operands. Okay, so it is completely, when the instruction is executed, we get the result. So store the result in proper place. So these are all this way it can be divided, right? Instruction cycle, the phases of instruction cycle can be divided. Let me give you an example. Generally, this example is given to understand this pipeline operation, like our daily routine job of washing clothes. So here, the task we want to do is washing clothes, okay? And it is divided. If we divide it into sub operations like washing, we put it in a washing machine, and what are the operations it perform? It performs washing and drying. So if the set of clothes are put, let's say that this washing takes some 30 minutes and drying takes 30 minutes. Okay, and this is the set of cloth. Okay, here we give it for washing. It is taken 30 minutes are taken to wash and 30 minutes are taken to dry. So what is the time? Total time taken here? 60 minutes. That is 1 hour to complete one cycle of washing. Okay, now let's say that we have a different batch of clothes to be washed. Okay, we have 2 or 3 sets of clothes to be washed. Okay, so that case, when we say this is set 1, instead of performing washing and after that, the same unit does the drying of the clothes. Okay, now it is separated. Here we are using it an example. So set 1 is put in the machine, it is washed, okay, in 30 minutes, and then it is moved to dryer for drying. At the same time here, when we can load set 2, once the washer is done, as these are now we are considering these 2 separate units, okay, 2 segments. One unit performs washing and the other unit performs drying. So when the washer is free, here washing is done, when it is moved to the dryer for drying, the next set can be loaded here, right, in the washer, okay, for washing. So when this is drying, the washing of this can be done. And once this dryer is free, once this is finished, we can dry the second set of clothes. So what is the total time taken here? Okay, if we do it parallelly this way, but the unit need to be free. That is why we don't load it here, because both already the cloth of set 1 is available here. Okay, it is being washed. So we will not load it here. What we will do is when the washer is free, when it is moved to the dryer, we wash it. Okay, we put the clothes for washing here. So the best thing is the resource, instead of waiting for the entire operation to be finished and to start the washing, okay, we are utilizing the unit that is available here. Same time, when the dryer performs this drying of clothes, washing can be done for the set 2, correct? So if you calculate the time here, this is 30 minutes for washing the first set of clothes, and the next 30 minutes, okay, in this 30 minutes, drying and the washing of this next set of clothes are taking place, correct? And another 30 minutes for drying of the second set of clothes. So this is, as we did this parallelly, the time taken is here 90 minutes, right? Totally 90 minutes are taken to wash 2 set of clothes. And the same thing if we perform with the non-pipeline unit. Okay, if these operations cannot be performed parallelly here, how much time it will take? We wait for the entire operation of this set 1 to be completed, washing to be completed, and we load the clothes in the machine in the next cycle only. Correct? Once the entire operation is finished, and another 30 minutes for drying. So the 30 minutes for drying the clothes. So the total time would be 120 minutes, that is 2 hours. Okay, so this way the time can be reduced. So this I just gave an example here to understand how performing the jobs parallelly when the unit is available, okay, reduce the time or speed up the process. Coming to this instruction cycle, they have divided it into the 6 phases. Now, if we assume that to make this process easier, let's consider a 4-segment instruction pipeline. Okay, we have divided it into 6 operations. So now let's assume that to perform this in 4 segments, fetching is done and then decoding is done with the this calculating the effective address is combined with this. Okay, so decoding, second phase is decoding and calculate the effective address. Okay, to consider a 4-segment instruction pipeline. So we are combining this, decode the instruction and calculate the effective address. And then the third sub operation would be fetch the operands from memory. Then next, execution and store the result in the proper place. Okay, once the execution is over, it is stored in the register or in memory. Okay, so let's combine these. And okay, let's assume that we have 4 sub operations. We have divided the instruction cycle into 4 sub operations. So here in this 4-segment instruction pipeline, the sub operations are instruction fetch, okay, denoted as Fi here. And the second sub operation is decode instruction and calculate the effective address. The third sub operation is operand fetch the operands for execution. Then the fourth operation is execution. Okay, instruction fetch Fi, decode and calculate the address. Okay, it is DA. Operand fetch, okay, FO, and execution EX. So if we in a pipeline unit, yeah, the entire process of execution is divided into sub operations now. So pipeline unit have different segments to execute these sub processes. Look at this table here. Instruction 1, first instruction. In step 1, in segment 1 at the first clock cycle, it is fetched. The first operation, sub operation is fetching the instruction Fi. Okay, so that is done. And when this moves to decode, okay, once the fetching is done, and then the instruction need to go for decode phase or finding the meaning of the instruction. So in decode phase, the same time when this is decoded, the instruction 2 will enter. Okay, so this can be fetched to perform this parallelly. How is it possible? Decoding of the first instruction and fetching of the second instruction. Here decoding is done inside it is an internal operation, okay, of the CPU. It is done inside the processor with the circuits for decoding available inside. There is no data transfer during decode phase. Okay, but here fetching the instruction needs a data transfer. It is not an internal operation. It is transferring transferring the instruction from memory to processor. So when when this internal operation of decoding is done, at the same time the bus is free. Okay, the bus that transfers the instruction is available and memory is free, not being accessed by any other instruction. So memory can be accessed for fetching the instruction. And now when this instruction 1 goes to the next phase, fetch the operand. This is a transfer type of instruction, right? Fetching the operand from memory. Okay, getting the operand transferring operand from memory. Okay, so here decoding is an internal operation. And again, here is a fetching. Here is a fetch and here is also a fetch. But this is instruction fetch and this is data fetch. For making this possible, fetching operand and at the same time fetching the instruction possible, memory units need to be divided because 2 memory access at the same time. That is not allowed. So here it is operand, that is data. So the data unit of memory need to be separated and instruction unit of memory need to be separately maintained. Okay, so that this can be done, fetching instruction and fetching the operand at the same time. Okay, so this way these operands are, so already we have discussed, okay, to implement parallel processing, the hardware need to be changed. We need to have a increased hardware and the complex control unit to manage all this, to control these operations. Now let's assume that the third instruction is a branch instruction. Okay, first and second are executed. Okay, some other instruction. And the third instruction is a branch instruction. Okay, you know what is branching, right? Okay, generally the instructions are executed one after the other. First, second, then third instruction and fourth instruction. Here, if third is a branching instruction, okay, we cannot say that fourth instruction may be executed or may not be executed. That depends on the branch. If it is, the branching may be conditional or unconditional. Okay, we have learned it in computer instructions. BUN, what is BUN? What is this instruction BUN? Nobody remembers this? BUN is branch unconditionally. Okay, there won't be a condition. Unconditionally, the branching is done. Okay, and B, somebody send the answers. 520, correct. Okay, branch unconditionally. Good. So BC, what is this instruction? BC, it is branch if carry. It is a conditional instruction. This is a BUN is an unconditional instruction. When this instruction is given with the address, okay, BUN followed by the branching address. Okay, we call it as target address. Okay, let's say TA. So branching will be done to the target address. This address will be loaded into PC so that the instruction at this location, target address, can be executed. And this branching can be done conditionally also. Okay, such as if we give BC, means branch if carry. The carry flag is checked. If there is carry, if this is 1, means there is carry, okay, from the previous execution. Okay, maybe if suppose the previous instruction 2 is some add, okay, it is add A and B. So if there is a carry out of this, carry flag will be set to 1. Okay, so here we check, we will have a branch instruction BC. Okay, so if there is a carry out of this addition, if there is a carry, we want to branch to some other location, some other instruction. Okay, so such branching, conditional branching also can be given. BC, BNC means branch if no carry, correct? Okay, so this way when we give B is it branch if 0, BN is it branch if not 0. This way conditions can be checked to branch. Okay, so if this third instruction is any of this branch instruction, based on the condition, branching may be done or may not be done. Okay, so the fourth instruction may be executed or it may not be executed. So, but the second here in the fourth step, okay, is the decoding of the branch third instruction. After decoding only, we'll know that if it is a branch or what is the type of instruction, because decode will get the meaning of the instruction. So until this decode phase is completed, the computer cannot do any operation. So the normal process F5 fetching of the fourth instruction will be done. Once it is decoded and it is understood that it is a branch instruction, now the control has to be taken to execute the target instruction in the target address. So this is halted here. Okay, so pipeline is made empty to perform that branching. The fourth instructions will not be executed here. It is the next instruction that will not be executed. The branching instruction at the target address need to be executed. Okay, so here pipe is emptied here. We will not execute this. and the branching target address is loaded into PC. So that instruction is loaded. This is the target instruction. Okay. Instruction at the target address that is loaded, fetched from memory, decoded and executed, and this continues. Okay, but if you see this part here, it is the units are not utilized, right? The resources are not utilized, and this part no operation is performed. Here this flowchart shows the operations what we have discussed here. Segment 1 performs fetch instruction from memory, and segment 2 does decode the instruction and calculate the effective address. Okay, the second sub operation DA, this is fetch instruction and decode instruction and calculate the effective address. And once the instruction is decoded, we check for branch. If it is a branch type instruction, update PC, program counter need to be updated. Okay, because the next instruction will be the target instruction, the instruction that is at the target address location. Okay, so here update PC with the target address, and then empty pipe, because next instruction will not be executed. To stop the execution of next instruction here, okay, empty pipe, and go to fetch the instruction. So that repeats, fetch the next instruction, decode, okay, and execute. So if it is not a branch instruction, fetch the operand from memory, normal execution. Okay, after decode, fetch the operand from memory and execute the instruction. Okay, this is fetch the operand and execution. This way, one instruction execution is completed. Once during execution of every instruction, there is there may be interrupt, okay, from some devices. So it is checked. If there is an interrupt, the control has to service the device, service the source that has initiated the interrupt. And for that, the interrupt service routine is executed. So if there is an interrupt handling, okay, what this does, it loads the interrupt service routine address of ISR into PC. Okay, so PC is updated and pipe is emptied. Normal execution will not be carried out. Okay, and that here this it goes back to segment 1. So the instruction that is fetched would be the first instruction of interrupt service routine in case of interrupt. And if there is no interrupt, go to fetch the next instruction. This is the sequential. If there is no interrupt in the sequential order, the next instruction is fetched, decoded, effective address is calculated, and operand is fetched from memory and executed. Okay, during execution of every instruction, the computer checks for interrupt. If there is an interrupt, that need to be serviced. If there is no interrupt, it can be repeated for all the instructions. Okay, same way after decoding, we check for branching. If there is a branch instruction, PC need to be updated and empty pipe, because the next instruction cannot be executed as normal. It has to go back to the instruction that is at the target address. That will be the instruction that is fetched here. If there is no branching instruction, continue execution. Here, as I said earlier, the branch instruction may be conditional or unconditional. And during decode phase, once this decoding is over, we will know whether it is a branching instruction or no, right? And if it is branch unconditionally, it will fetch the next instruction from the execution of this instruction will make the PC uploaded, and this is emptied, pipe is emptied, and the next instruction that is at the target address would be fetched, decoded, and executed. Correct? And in case of conditional branch instruction, the condition may be true or false. Okay, so after this execution, if the condition is false, then this fourth instruction need to be executed. Okay, if the instruction used is BC, branch if carry, but the carry flag, let's say that the carry flag is 0. Okay, so it is not true. So this case, branching will not take place, and the instruction, fourth instruction will need to be executed. So it is already fetched during the decode of this third instruction. Fetching phase of this is done already. Okay, so here we will not carry out this. Here the next operation would be decode. Already fetching is done. So decode the instruction and then fetch the operand and execution. So this way, this branch instruction changes the normal operation of this pipeline unit. So what are the difficulties here? The three major difficulties that cause the instruction pipeline to deviate from its normal operation. Normal operation is executing the instructions one after the other in a smooth way. But there may be conflicts. Okay, so the three major difficulties are resource conflict. First one is resource conflict. This is caused by access to memory by two segments at the same time. As we discussed here, if these two come in the same line here, fetching the operand and fetching the instruction is performed at the same time. So memory access is needed for both of these part of instructions, right? Fetching the operand means data need to be fetched from memory, and fetching instruction need to be fetched from memory. So at a time, both these instructions need memory access. Okay, so this can be resolved by separating the instruction and data memories. Okay, instead of having a single memory unit for instruction and data, if we have two separate memory units, one for instruction and one for data, and two separate bus lines for transferring those instructions and data separately. The memory that have the instruction will be connected with CPU with a separate bus, memory bus, and memory unit that stores the data gets connected to the CPU with another separate memory bus. Okay, so this way, increasing the hardware units, we can resolve this issue of resource conflict. And the second difficulty is data dependency. So here this dependency arises, okay, this conflict arises when an instruction depends on the result of the previous instruction. Okay, if suppose two instructions are here, these conflicts arise because these instructions are executed parallelly. So if suppose the result of this instruction 2 is executed, let's say this is add instruction, and the result is stored in A. A and B are added and result is stored in A. And that A is needed for executing the third instruction. Okay, so unless this entire operation is completed, executed, this cannot be performed. So here this third instruction need to wait for obtaining the result from the previous instruction. Okay, here the result is not available, but this instruction need the result of the previous instruction for its completion, okay, for its execution. So this conflict also can arise. And the third one is what we discussed here during branching. Okay, branch difficulties. The branch instructions that change the order of the instruction execution. So there the resources are not utilized and kept empty for more time. Okay, pipe is empty. So this changes, when the execution order is changed. We may have this difficulty. Okay, so we need to have a way to resolve these issues. Okay, when pipeline is used, system is anyway made complicated than the normal performing normal operation. So we need to have way to solve these issues also. Let me summarize this. We have discussed about arithmetic pipeline and instruction pipeline. Arithmetic pipeline, this unit helps the computers to perform the arithmetic operations, subdividing the arithmetic operations into smaller sub operations and executing them parallelly in different segments. Okay, any operation that can be divided into sub operations can be executed parallelly in different segments. That speed up the process. So we have taken an example of a floating point addition and subtraction. This floating point addition and subtraction can be divided into four sub-operations. Compare the exponents. The exponents need to be equal, okay, for performing addition or subtraction. So compare the exponents and choose the exponent, align the mantisas and adjust the exponent accordingly to make it equal, okay, to make it equal as A is equal to B. And once this is done, add or subtract the mantissa, then normalize the result. Okay. If there is an overflow or underflow, we need to normalize the result. So here A and B are this is the exponent part, small a and small b, and capital A and B are the mantisas, okay, mantissa part of this x and y. And first segment performs the first sub operation, that is compare the exponents. That is done by subtracting the exponents. Okay, so A minus B is performed, and based on the result, if the result is positive, means A is first exponent is greater. If the result is negative, means the second exponent is bigger. So we choose the exponent and accordingly align the mantissas. And once that is done, perform in segment 3, perform addition or subtraction depending on the requirement. And segment 4 normalizes the result. Okay, so here when we normalize, when we shift right or left the mantissa part of the number. Okay, so when it is shifted right, the exponent need to be incremented, right? And when it is shifted left, it need to be decremented. According to this okay operation, normalizing the result, exponent need to be adjusted. Okay. And the second type of pipeline, instruction pipeline, that allows the instruction to be executed in different phases and parallelly running in different segments. When the decode of the first instruction is carried out, the second instruction can be fetched from memory. Okay, so this way parallelly these different operations, okay, that are in different phases can be done in different segments. So we have taken a 4-segment instruction pipeline. First segment performs instruction fetch, and the second segment, decoding the instruction and calculating the effective address is done. And in the third segment, fetching the operand, and in fourth segment, execution of the instruction is done. Okay, so here if we take instruction 1, fetch instruction, then the second phase, it goes to the segment 2. Okay, segment 2 does the decoding of the instruction. And segment 3, fetching of the operand. Segment 4, execution. And once during the decoding, okay, in segment 2, when segment 2 decode this, at the same time, fetching of the next instruction can be done. Okay, so this way, parallelly different instructions are executed at the same time. And if the next instruction, if it is a branch instruction, it has to stop the sequential execution, and the control has to jump to the instruction at the target address. Okay, so this instruction, fourth instruction, will not be executed. So the pipe is made empty here, and once the target address is found, located, that instruction from the target address is executed. Okay, here is the flow of the operations. Fetch the instruction from memory, okay, in first segment, and in second segment, decoding the instruction and calculating the effective address is done. And once it is decoded, we check if it is a branch instruction. If yes, update PC with a new address and empty pipe and go to fetch the target instruction. And if not, if there is no branch instruction, fetch the operand from memory, normal execution, okay, and execute it. And we also check for interrupt. If there is an interrupt need to be handled. Okay, so same operation. We need to update PC and empty pipe because this also stops the interrupt the normal execution. Okay, so pipe need to be left empty and it goes to execute the interrupt service routine. If there is no interrupt, okay, go and fetch the next instruction in sequential order.